Hello viewers, in this unit we will talk about the communication protocols of Internet of Things which form the backbone of IoT systems and drive the technologies that enable IoT applications. Such protocols are fundamental to extend the Internet communications infrastructure to incorporate constraint sensing and actuating devices, thus enabling what we refer to as the IoT. Let's first understand what is a communication protocol. A communication protocol is a set of rules and conventions that define how data is exchanged between devices or systems in a network. These rules specify the format, timing, sequencing, and error checking of data transmitted over the network. In the conventional internet architecture, protocols are essential for ensuring that devices from different manufacturers or developers can understand and interact with each other in a standardized way. Similar to the traditional internet, the communication protocols of IoT allow IoT devices to exchange data amongst themselves and with other devices and systems over the internet. Therefore, by the end of this unit, you will be able to explain the need of a novel communication protocol stack in IoT, describe the standardized IoT communication protocols, their design considerations, some security and research challenges, and perform the implementation of these protocols in the Contiki operating system, that is an open source OS for IoT. Now let us understand why existing communication protocols cannot be directly used in IoT. The existing internet protocols were designed for computer systems with the relatively powerful processors having abundant storage space. And a typical implementation of these protocols involves large, complex headers and excessive metadata, the need for reliability through packet acknowledgement and transmission of unneeded data. These protocols' operations are resource intensive and require a lot of energy on the communicating system. Thus, they cannot be directly implemented to run over low power communication networks where energy is a constraint like IoT, which includes a majority of embedded resource constrained devices with limited processing power and resources. So, these IoT devices would require new protocols more suited for the constrained environments. We can now define the core requirements for an IoT protocol stack. The core requirements for an IoT protocol stack is that it must be low power, that is, it must utilize minimum resources of the device. It must be highly reliable, that means it must ensure reliability of the communication. And it should be internet enabled, that is, the ability to communicate with the existing systems and devices on the internet, and it should be open and standardized to ensure interoperability. Before we dive into specific protocols, let's briefly discuss why standardized communication is essential for the Internet of Things. In an IoT ecosystem, devices need to communicate seamlessly for efficient data exchange and interoperability. Standardized communication protocols ensure that devices from different manufacturers can work together seamlessly. This interoperability is crucial for creating an unified and efficient IoT ecosystem. Initially, the early design of protocols for IoT traced back to extending the protocols of wireless sensor networks. However, such protocols were very company specific with proprietary hardware and communication stack. The standardization bodies like IEEE and IETF quickly recognized that having a multitude of proprietary systems connected to the internet does impede the scalability and explosion of the IoT. And since 2003, the standardization bodies started putting together a framework to communication protocols to the emerging systems. The consistent research in this area led to the development of the standardized IoT protocol stack, which we will now discuss and compare it with the conventional internet stack. The protocol stack consists of the following layers. First is the link layer, which defines how to share medium and send communications in the network. While we have Ethernet and Wi-Fi protocols in the conventional internet, we have a novel protocol, that is IEEE 802.15.4 in the Internet of Things. IEEE 802.15.4 is a standard for wireless communication that defines the physical and MAC layers. It is standardized by IEEE, just like IEEE 802.3, that is for Ethernet, and IEEE 802.11, that is for Wi-Fi. The 802.15 group of standards specifies a variety of wireless personal area networks like 802.15.1, that is Bluetooth. The IEEE 802.15.4 focuses on communication between devices in constrained environment with low memory, low power and low bandwidth. Second is the internet and the routing layer, which is responsible for information relaying and routing in the network. In both conventional internet and IoT, IPv6 protocol is implemented, but as far as routing is concerned, IoT has a novel lightweight routing protocol called the RPL, which we will discuss about RPL in detail in the next video. Interestingly, a new protocol layer is defined in IoT below the internet layer, which is called the adaptation layer. The responsibility of adaptation layer is to compress, fragment and reassemble the IPv6 data packets adapted to IoT constraints. Since an IPv6 packet is too large to fit in an IEEE 802.15.4 frame, the adaptation layer compresses and fragments the IPv6 packet to make it suitable for link layer which supports similar size frames. Next is the transport layer. The transport layer provides the communication services directly to the application, and in the conventional internet, both TCP and UDP protocols can be used. However, TCP is not included in IoT protocol stack as it incurs a lot of energy overhead due to its reliable and connection oriented nature. And therefore, UDP, being an unreliable, connectionless and lighter protocol, has been accepted as de facto standard in IoT. The data presentation and formatting happen at the application layer. In the internet stack, HTTP is used, whereas in IoT, COAP protocol is used, that is known as COAP. So, COAP is a specialized web transfer protocol in IoT with smaller header sizes compared to HTTP. The design goals and architecture of COAP will be discussed in the next video. From the discussion of standardized protocol stack for IoT, we came across some novel protocols specifically designed for IoT. We have now understood that these protocols were developed to facilitate the integration of low power wireless networks into the internet. Now let's explore some of the key standardized communication protocols in the world of IoT. We'll discuss 6LoWPAN, RPL and COAP. First is the 6LoWPAN protocol, which is the acronym for IPv6 over low power wireless personal area network. As the full name implies, 6LoWPAN is a networking technology of the adaptation layer that allows IPv6 packets to be carried efficiently with small link layer frames such as IEEE 802.15.4. 6LoWPAN was developed by the IETF in 2007 to work on specifications for transmitting IPv6 over IEEE 802.15.4 networks and is now an open standard defined in the RFC 6282. Now let us first understand the challenges of supporting IPv6 over IEEE 802.15.4 networks, which led to the development of 6LoWPAN. IPv6 covers an address space of 2 raised to the power 128 unique addresses, and to recognize the increase in bandwidth, the minimum maximum transmission unit, which is called the MTU, was increased from 576 bytes in IPv4 to 1280 bytes in IPv6. Though this MTU size is suitable for conventional link layer technologies like Ethernet and Wi-Fi, it is extremely large for IEEE 802.15.4 link layer, where the throughput is limited to 250 kbps and the frame length is limited to 127 bytes. Clearly, IPv6 datagrams are not a natural fit for IEEE 802.15.4 networks. Low throughput, limited buffering and datagrams that are nearly 1/10 of IPv6 minimum MTU make header compression and data fragmentation a necessity. Since IEEE 802.15.4 is both low power and low throughput, it requires the network layer to be adaptive and responsive, at the same time low power and efficient. The above issues are all addressed in the 6LoWPAN standard, and now we will discuss how 6LoWPAN addresses these issues. First is the header compression. 6LoWPAN compresses the IPv6 header to reduce the packet size by assuming the usage of common fields. Some common header fields are removed when they can be derived from the link layer. Second is the fragmentation and the reassembly. 6LoWPAN fragments the IPv6 packets and sends it through multiple smaller size packets that can fit in an 802.15.4 frame. On the other end, it reassembles the fragmented packets to recreate the IPv6 packet. For this purpose, an additional fragment header is used to reassemble the packets in the correct sequence. When the data packets are reassembled, the additional header is removed and the packets are restored to their initial IPv6 format. To understand this clearly, let us look at the 6-LoWPAN network architecture. In this figure, we can see that the uplink to the internet is handled by the access point acting as an IPv6 router. Several different devices are connected to the access point in a typical setup such as the PCs, the servers, etc. The 6-LoWPAN network is connected to the IPv6 network using an edge router. We can also see that the edge router implements the dual protocol stack, one for the traditional IP network and the other for the 6-LoWPAN network. The edge router handles three actions: the data exchange between 6-LoWPAN devices and the internet, local data exchange between devices inside the 6-LoWPAN, and the generation and maintenance of the 6-LoWPAN network. Let us look at the advantages of 6-LoWPAN now. It is compatible with open IP standards like TCP, UDP, HTTP and CoAP. It offers end-to-end IP addressable nodes. There is no need for a gateway, only a router which can connect the 6-LoWPAN network to Internet protocol, that is the IP. It supports self-healing, robust and scalable mesh routing. It also offers one-to-many and many-to-one routing. In a 6-LoWPAN network, leaf nodes can sleep for a long duration of time. Another powerful feature of 6-LoWPAN is that while originally conceived to support IEEE 802.15.4 low-power wireless networks, it can also be adapted and used over a variety of other link layer technologies including low-power RF, Bluetooth Smart, power line control and low-power Wi-Fi. However, some challenges in the implementation of 6-LoWPAN are: the current 6-LoWPAN specification only discusses general security threats and requirements. However, no specific security mechanisms have been adopted so far for the 6-LoWPAN. Apart from that, 6-LoWPAN is susceptible to packet fragmentation attacks also. Lastly, the standard does not propose any specific key management solution which is considered a cross-layer security aspect and interrelated with authentication, since the keys must be negotiated and periodically refreshed in order to guarantee effective and long-term security. Hence, these security challenges must be addressed before the implementation of 6-LoWPAN in real IoT networks. In conclusion, 6-LoWPAN is a key enabler of the IoT revolution. It bridges the gap between diverse devices, paving the way for a seamlessly connected world. Thank you. In the next video, we will learn in detail about the routing and application layer protocols for Internet of Things.